Okay, why don't we start? So, hello and welcome everyone to the Ethereum Engineering Group meetup. Today, Raghavendra and myself are going to talk about yep, there we are. We're going to talk about cross-shard communication in Ethereum 2 and all the various mechanisms that have been proposed. This is the 50th meetup that we've done. So we've done 50 of these across 2.25 years. Yes, I know. That's a big round of applause or something, or is that a Mexican wave there, Horacio? Yeah. So anyway, it's fantastic that we've, I think a massive achievement that we've made it this far. So let's see if we'll make it to 100. So anyway, I think Raghavendra is going to do the first half and I'm going to do the second half. So over to you, Raghavendra.
Thanks, Peter. Let me start with the agenda slide. So here's the outline. We'll discuss the problem first and the problem of cross-shard transactions in Ethereum 2 world. And then I'll review some of the techniques that are proposed. I'll take the asynchronous world first, and then Peter will continue with the reviewing the existing synchronous techniques, as well as presenting his original proposal for atomic cross-shard transactions. Okay, let's begin. Okay, the problem. So in Ethereum 1 world, it supports the ETH transfer. That is, if you want to transfer X amount of ethers from Alice to Bob, then anyway, it supports two things mainly. One is Ethereum ETH transfer. The second one is function calls on a contract. There can be cross-contract function calls as well. The main features are these ETH transfers or the cross-contract function calls. They are executed in one transaction, and they are executed atomically, and this yields for composable programming as well. However, in the Ethereum 2 world, we have this scenario. We have a beacon chain, and we have 64 other shards, which actually distribute the state and the transaction history. And blocks are proposed in every slot, and there are 32 slots in every epoch. And beacon blocks and shard blocks go hand in hand. I'll explain that specifically in the next slide, but we'll have that in the background. And there is this notion of execution environments. Execution environments very flexibly capture the idea of state transition. In the Ethereum 1 world, the state transition is kind of hard coded, but in the Ethereum 2 world, one can define, or one can come up with their own state transition and define an execution environment for it. So that means we can have an execution environment modeling the current ETH1 world. We can have an execution environment modeling the UTXO model of Bitcoin and many more. And the user accounts exist within these EE instances, which are, again, there are different instances running on shards. And the execution environments need to maintain its balance, ether balance. That's not globally kept in one place or in the beacon chain, it's distributed. So every shard for every execution environment instance maintains its balance. Okay, so this is the backdrop. And we need one more concept called Merkle trees and Merkle proofs. This becomes more and more prominent in the Ethereum 2 world. So let's just review that concept. So suppose we have this data split into chunks from D000 to D001, D010 to D111. And a tree can be built with hashes. This is called a Merkle tree. So you have H000, which is a hash of D00, and correspondingly the others. And we take hash in the next level, hashes in the next level, and finally we have one specific hash that we call root hash. Okay, so this captures the integrity of the data. The root hash, in fact, captures the integrity of the data. And in fact, in order to communicate a particular data element, let's say I want to send to a different chain in the Ethereum 1 world or in the different shard in the Ethereum 2 world, the element D000, that is the first leaf, then I would send that. And in order to prove that I have not forged it or not changed it, I'll have to send a proof as well. The proof would entail these hashes. So the recipient can get my information, that is D00, and compute its hash H00, and I would give the proof, which is the red boxes, H001, and he can compute H00 from it. And taking H01 from my proof, he can compute the H0, and taking again H1 from the Merkle proof that I have provided, the recipient can compute the root hash, and he can match the root hash with a secure place where the root hash is stored. So this is how a communication can be established using Merkle proofs and root hashes. Okay. So another key concept in Ethereum 2 world is the notion of crosslinks. So this diagram illustrates this notion. So imagine we have beacon blocks churning out in the first row, the topmost row, 8, 9, 10, 11, 12, 13. And there are multiple shards described here, shard 1 to shard 7. In fact, we'll have 64 shards. And these shards will also churn out blocks every slot. So 7, 8, 9, 10, like that. The notion or the interesting concept here is, let's consider the post state of the shard 1 after executing block number 7. So that the Merkle root of that state is kept in the beacon block number 8. In fact, that's precisely what is called as a crosslink. So crosslink is just nothing but a Merkle root of the post state of a shard. In fact, the beacon block will maintain 64 such crosslinks, one for every shard. So is that clear to everyone? Yep. So as I said, let's look at this application app towards the bottom of the diagram. So it can submit a transaction on shard 1. Okay. And the application will submit, let's say, other transactions on shard 5 and 6. But the application wants to communicate some information from the first transaction to second and third transaction. The way for the application to communicate that is to give the data to the shard 5 and 6 and also produce a Merkle proof of the post state after the shard 1 block 7. And the block proposers on shard 5 and 6 can use that Merkle proof and the data provided by the app and can check the crosslink for the Merkle root and establish the sanctity of the data. And that's how the communication happens. So this is an important part for the cross-shard communication. I hope it's clear. With this background, let's delve into what exactly is the problem. As we saw in the Ethereum 1 world, transferring ETH was just one transaction. Okay. In this case here, because we have different EE instances on different shards, this transferring of ETH can be split into 4 action items. Suppose we want to transfer from Alice to Bob, X amount of ethers, then we need to debit X from Alice user account, which is an account existing on an, let's say, EE1 instance on shard 1. Also, the EE1 instance, which is maintaining its own balance, has to lose X amount of ether. So debit X from EE1 instance on shard 1. Next, or credit X ethers to EE2 instance on shard 2, and then credit X ethers to the Bob account, which exists on the EE2 instance on shard 2. So this specifically illustrates or shows that the transfers comprises two separate transfers. One is at the user level, the other one is at the EE level. Okay. So in terms of contract calls, hotel train problem is a representative problem to showcase cross-shard contract calls here. Imagine that we need to book a hotel room as well as a train seat, and the hotel contract exists on a one shard and the train contract exists on another shard. The requirement of this hotel train problem is to atomically book a hotel room and then a train seat. So these are the main two problems that we'll concentrate for the rest of the talk. Okay, so let me review some of the asynchronous techniques that were proposed.
We can't hear you, Raghavendra. We lost audio. No, can't hear you.
Am I audible now?
Yes.
So the same problem happened again. Okay. So the general approach for cross-shard ether transfer is, or asynchronous way of cross-shard ether transfer is to use receipts. So the ether transfer transaction is split into two, a debit transaction and a credit transaction. And the outstanding credit transaction is termed as a receipt, this word. And also note that this entire set of approaches that I described, they solve the problem only for the E level transfer, not the user level transfer. User level transfers are left for people after the E level transfers are settled. Anyway, so let's see this case. We have two shards, shard M and shard N. There are four users, A, B, C, D. A and C exist on shard M. B and D exist on shard N. A has 500, C has 730 coins. Suppose we want to transfer from A to B 100 coins. Now, that was the state here in this shard state. Imagine that these are the square ones are the beacon blocks. Now, yeah, so we will do the local debit transaction first on the shard M, that is deducting 100 coins from A, and the pending credit of 100 coins to Bob or B is kept as a receipt or stored as a receipt in the state. And that is communicated, as I said before, using the beacon block for shard N. At this shard block, nothing can be done because they are happening at the same time. In the next block and shard N, it can process that receipt. So the receipt 172, etc. is processed here, and B is credited with 100 coins. And it will have to send again a Merkle proof saying that the transfer has been complete, so that the sender shard, the shard M, can go through. So this is the general idea. So digging deeper, Vitalik proposed the idea of sequential receipts on the October last year. The idea here is every shard maintains in its state for every other shard B 2 nonces. S stands for send and R stands for receiving nonce. So sending nonce AB, that is sending from A to B, saying that this nonce should be included in the next receipt that will be sent from A to B. Receiving nonce RBA is an expected receipt. So the receipt that is coming from B to A should have this nonce RBA. Okay, let's look at the mechanism. Suppose I want to send from A to B, the shard A will create a receipt containing SAB, this nonce. and it will locally increment these nonce. And on the shard B, the block proposer among the many receipts in the mempool will look for a receipt specifically matching the nonce RAB. Okay, when it finds it is included in the nonce, included in the block and is processed, and he locally increments the receiving nonce RAB. This is pretty much the idea of this approach. The main disadvantage is the sequential processing. That means even though, let's say there is some malicious application which will delay putting this receipt in the mempool of the recipient shard, then all the receipts that are waiting further in the queue, they are delayed as well. So that is the main disadvantage. And so hence, next proposal by Vitalik was for processing receipts in a non-sequential way. This was in December 2019. Before going through this proposal, let's understand more about the way receipts are used in this approach. So as I said, receipts are nothing but outstanding credit transactions. They are stored in the sender shard as a key value map. Key being the recipient shard and the recipient execution environment, and the value being the transfer amount. So it is stored in the sender shard state as a modified Merkle-Patricia tree. We need to understand another notion called Bitfield tree. The reason these Bitfields are used on the recipient shard is to ensure that the receipts are claimed only once. Let's say on a shard, on a slot n in the sender on the sender shard, there are multiple receipts targeted for a single recipient shard. These receipts would update multiple EEs on the recipient shard. This approach constrains that all receipts targeted for a specific shard need to be processed together. That means it would involve updating multiple EE balances. So all those transactions would necessarily have to be included in the same block, the same slot. So again, these bitfields are maintained as a key value map, which is from the sender slot to a bit value 0 or 1. 0 signifying that none of the receipts from the sender shard on the sender slot, on this particular sender slot, is processed. 1 saying that all of them have been processed. One natural question here is why to flip the bit to 1 and keep it around. When the receipt is processed, it is done. Then one can delete the entry. The idea here is, again, just to recall that this is illustrating only the E level transfer and the user level transfers are still pending, so that the user level transfer can happen in the subsequent slots. So that's why this only shows that the E level transfer is complete. And once the user level transfer is also complete, this can be kicked out. Okay. So let's work through this approach using an example. Again, let's suppose that the shard 1 E1 wants to transfer X amount of Ether to shard 2 E2. Then on the shard 1, application puts this local debit transaction in the mempool. It also constructs a receipt tree if it does not exist already. If it exists, then it will add this receipt, which is nothing but the outstanding pending trade transaction, to this receipt tree, which is like shard 2E2X. And block proposer, let's say, picks up this local debit transaction, which is debit Xeth from E1, and he'll have to include the receipt transaction also in the same block. And then just to ensure that the receipt trees are maintained or not tampered with, he'll have the Merkle root of the receipt tree, and the updating of the balance is happening. Updating of the E1 balance is happening correctly. So we'll have the Merkle proof of E1 pre-balance and also the Merkle root of the state showing the updated EE1 balance in this block. And the application waits for the next beacon block, which will include the cross-link for the updated state on shard1. Okay. Now, again, I described one way of communicating receipts previously. Now that the receipt has to be communicated to the shard2, there is another notion that people have come up with, or people understand that the receipts can be communicated using beacon blocks as well. Just put all the receipts in the beacon block. This idea is used by the simulator that's developed by Joseph DeLong from Pegasus Consensus. This simulator demonstrates this particular approach, the non-sequential receipts approach of Vitalik. But the problem with this approach is its impracticality, meaning that that means that the beacon blocks can grow in an unbounded fashion. That may not be practical. The other way is what I have already described, that the application actually submits this receipt on the recipient shard along with the Merkle proofs. Okay, so we saw on the sender shard what happened. Let's look at what happens on the receiving shard. So the application puts the receipt transactions in the mempool, to the mempool, and it constructs a Bitfield tree in the shard2 state. If it does not exist already, if it exists, then it just adds one entry.
Your audio stopped working again.
Able to hear you, Peter. Can you repeat that?
Yeah, I can hear you now.
Okay. If it happens again, then I'll check the speakers. Okay. So I'll just go through again. So application puts the receipt transaction to the mempool of shard2. It constructs a Bitfield tree if it does not exist already, or if it exists, then it will just add one entry to the Bitfield tree, saying that the shard1 has a receipt in slot n for this shard, and that's initialized to 0. So block proposer on shard2 creates a block with including this receipt, which is like credit X ether to EE2, if this Bitfield is set to 0. Then it also includes the Merkle root of the updated Bitfield tree. It includes the Merkle proof of the pre-balance of EE2 and the Merkle root of the updated EE2, just to show the sanctity of this credit transaction. It will also include the Merkle proof of the receipt tree from the source shard, just to say that this receipt was processed in this slot. So finally, this slot on the shard2 happens. The beacon block, we'll have to wait, the application has to wait for the beacon block, next beacon block, which includes the crosslink for this shard2. And then the shard1 will know that this transaction has been completed and it is free to proceed with either user level transfer or anything that it wants to do. So that is in a nutshell this approach. It's not described in as detail that I have described in the original post. So I have filled in the gaps. So the main advantage from the previous approach is the non-sequential processing of receipts. So the block processor does not have to wait for a specific receipt. It can include as whichever receipt it wants to include to the block. The disadvantage is that the receipt tree and the Bitfield tree have to be maintained. So anyway, we do kick out the entries in the Bitfield trees and the receipt trees once the processing is complete, but there is no size limit on these trees. If it depends on the pending receipts that are out there, which is unbounded. So this is the major disadvantage. Okay, so another approach was published by Vitalik again, late December last year, mainly to overcome these disadvantages. disadvantages of sequential processing and the disadvantages of keeping receipt trees and Bitfield trees around. So the main idea of this approach is not to have one single balance of the E on shard, but to distribute it across it. So that means that globally, for every execution environment, a matrix is maintained, shards cross shards, showing the balance of this E on various shards. However, this global matrix is not stored in one place. They are stored in a distributed fashion. That means every shard will have its row. So you have rows for A, B, and C. Those are kept respectively in shard A, shard B, and shard C. So the real balance of execution environment on a particular shard is got by summing up that column. For example, if I want to have the balance of this execution environment on shard B, then I'll have to sum up the entries in the column second, which is the B column, 10 plus 5, 15. As I'll describe later, the diagonal elements can go negative as well. Okay. So let's describe the mechanism. Again, we take up the same example. Let's say shard 1, E1 wants to transfer X amount of ethers to shard 2, E2. So everything happens on the sender shard. That means on the shard 1. There is no processing required on the shard 2. That is the beauty of this approach. So on shard 1 in the slot, it will have to first check that for enabling this transfer, this EE1 has X amount of ETH. The only way to check that EE1 on shard 1 has at least X ETH is to query all other shards, because remember that we need to sum up all the columns. We need to query all the other shards. Querying meaning that the shards have to send their version of the balances or their portion of the balances along with the Merkle proof saying that whatever I have sent is correct. So it needs Merkle proofs from all of the 63 shards. And once this check is passed, that the real balance of E1 on shard 1 is more than X, then all we have to do is update locally on the source shard. Now remember that on shard 1, all I'm describing, all the tables here are on the shard 1, nothing on the shard 2. So shard 1 has 2 rows, one specifically for E1 and one row specifically for E2. So this is for the before executing this transaction. This is after. Again, this is before and this is after. So for E1, let's suppose that the shard 1, the state has A1, A2, A3 entries. Then we will deduct A1, we'll deduct X from A1 for this entry. And for E2, we will just credit that X to the shard 2. Again, because the E balance is not stored in one place, but is distributed across shard, we don't have to do anything on the recipient shard. The transaction is done. Everything has happened locally at the sender shard. If E1, so if the A1 is less than X, this can go negative. The real balance can still be more than X, but the local portion of what's happening? So the local portion can still go negative. Okay. So that is.
Yeah.
David, do you have a question?
Yeah, could you go back one slide, please, Raghavendra? So this has the rather odd property that reads are actually more expensive than writes. Is that correct?
Yes, that's correct.
That's a very uncommon property to have in a system like this, but I see why it's done that way.
Yeah, yeah. I think there have been some proposals, or you can say tuning of this approach, where you query or you get the Merkle proofs from other shards only till the point that you can sufficiently prove that the real balance is greater than X and no more. That's one. And the other optimization is to cache the portion of the balances that are there on the other shards. But I'm not sure. Like one needs to maintain again that the caches are consistent and.
Yeah, I'm not. I think though this before you can do a write, you always have to do a read. Hence, writes must cost more than reads, because to read a balance, you've got to do a Merkle proof from 63 other shards. So that's, and then to do a write, you need the Merkle proof from 60 other three other shards, plus you do the transaction to update the state.
No, the writing is happening in the same slot where the checking of balance is done, right? So once you have the Merkle proofs from all of the 63 shards, and once the check is passed, then we update in the same transaction.
Yeah, but I think David was saying overall there's more work, networking CPU involved in read than write. No, I think, David, was that what you were saying?
It is, and I take your point, and I think that's true only if that transaction is in isolation. You might conceivably do one read and then several writes based on that information you have. You
Yes,
wouldn't
yes.
necessarily do a read across 64 shards prior to making a change if you've just done a read.
Yes, so another dimension is that this E level transfers. So the user level transfers are let's say are batched together. So there is one E level transfer for catering to a multiple user level transfers.
Yeah, so the truth is somewhere in the middle, I think, as is so often the case.
And the thing I think about this, especially this one, is the actual user level transfer. So communicating from an EE on one shard to an EE on another shard, which user's account should actually be updated with the balance, increased balance, is just left as an exercise for the reader, which feels like a really complicated learning exercise.
Yes, true. Okay, so the main benefits of this approach is that the update is done in one slot atomically, and we don't have to maintain any receipt trees or Bitfield trees. And the receipts are processed in a non-sequential fashion. So that pretty much sums up this approach. So there is one other proposal that I would like to cover in this presentation. This is using ETH transfer objects proposed by Casey, February this year. So the idea here is not to burden the blocks, but to have everything done in the state. So let's say this is the status of the sender state. So we have, again, we want to transfer 5 ethers from Alice. Sorry, no, I think we're sending, we'll be sending only 1 ether.
Yes, I think you're sending 3 ether from Alice to Bob, but it doesn't say that on this.
On the screen, okay. So this is the state held. State includes the balance as well as the nonce. And when we want to transfer 3 ether, then we create a ETH transfer object in the Alice state. That ETH transfer object will have the transfer to the amount to be transferred, not exactly balance, it's actually the transfer amount, and the status of the transfer. So once we have that in the state, the Alice state has updated, the entire shard state has updated, and that goes to the crosslink in the beacon block. And in the next slot, this object is presented to the Bob's shard, and Bob will create the same object, but this time with the transfer status as done and affecting the transfer. Note that in the previous step, the balance was decremented. The Alice debit happens, debit to Alice, and here the credit to Bob happens. Now he will have this ETH transfer object in his state.
Yeah, I think it's worthwhile mentioning that that ETH transfer object is passed in as part of the transaction, as well as the Merkle proof to prove that it exists on Alice's state tree. So yeah.
Yes. So the application has to include the ETH transfer object in the credit transaction, as well as the Merkle proof saying that the Alice state, yeah, contains this object. Yep. So the next step is to clear up these ETH transfer objects. So in a subsequent slot, Alice will first destroy this object after looking up to the Bob state saying that the status has been done, or using the crosslinks. And then in the next subsequent slot, again, the Bob gets to destroy his ETH transfer object. Now the transfer is done. Yep, using precisely the state space. So the replay protection here is the Bob's object is created, can only be created if Alice object exists in the previous slot, and Bob does not have it. Again, the deletion of ETH transfer object is also sequenced, so the Bob can delete it after Alice. Yeah, so the main advantage is all the information is stored in the shard state, and it would take 2 slots to affect the transfer. The main disadvantage is it would take 2 slots to affect the transfer compared to the netted approach. With the netted approach also would need 1 more slot for the application to create balances, read the balances from other shards and send it. And it has additional transaction types needed for cleanup. So this is pretty much the review of the asynchronous techniques that are out there. I think we can save the question for the last, because we are already 40 minutes of the presentation, and we can proceed. I'll hand over to Peter for synchronous techniques. Let me stop sharing, and Peter can share his slides.
I think I'm sharing my screen. Can everyone see my screen? Yes, I get some thumbs up. This is good. This is good. And yeah, so I'll put participant view. All right, so cross-shard. So the first technique is cross-shard yanking, which Vitalik came up with a very long time ago, almost 2 years ago. And so the idea is that you can move a contract from one blockchain or one shard to another shard. And you do that using a special EVM transaction, or some special mechanism. And so you yank your contract from one shard to another. So it's no longer available, say, on the hotel chain. And so the code and data are moved across to the train chain. And then the train and hotel contracts are now on the same shard. So you book your seat and your hotel room. And then you push the hotel contract, including the state, back over. And so this is where the thought was, well, you wouldn't want to, you're essentially, when you're yanking a contract from one shard to another, you're effectively locking it. And so you don't want to lock a whole hotel. So maybe you would split the contract up into hotel rooms and a main hotel contract. And so there's all sorts of timeouts and using Merkle proofs to prove that things have happened or not happened with this technique. And so at various times there's been a gas fee depending on the size of the contract, and then there's been a thought that you'd have a fixed size contract that you had to do. So the underlying technique has changed around a little bit. But it does let you do synchronous atomic function calls, which is good. Some people seem to get worried about the fact that, well, when the contract's locked and it's not on the original chain, then it's not available for use. And so some people thought that was a problem. You can only do one level of call graph with this. So you can only do a function on one contract on a shard that calls a function in a contract on a different shard. I don't think there's a mechanism to do a multi-level call graph with this. And that last one is something that Raghavendra wrote in, where I think at the larger the state, if you had a really large state size, then trying to move it from one shard to another shard would take a lot of time, would be a really bad idea. Is that it, Raghavendra?
Yeah, I mean, if the time bound for the yarn contract to be usable on the destination shard is longer, then the state that you need to store it for many, if there are many contracts in the line, then you would have to accumulate larger state size.
Okay. So another mechanism that Vitalik came up with a bit after this was a simple synchronous transaction protocol. And so the diagrams to this methodology on research are broken, so they're not there. And so the mechanism is actually pretty confusing. And it also relates to a different era of Ethereum architecture, which again is a little confusing. However, what I've worked out is, and trying to reinterpret it for the current era of Ethereum 2. For each transaction on shard, you look at it and you determine what it references that's external to the current execution environment. So you work out what other shard it might use and what the address within an execution environment it uses. And so you fetch the data value and you determine the Merkle proof that proves the result of that data value on the other shard. So if you've got a data value somewhere, you can do a Merkle proof given it's in the state, use the cross-link to prove that that is the correct value. And so then on the original shard, you execute the transaction and you supply all this information about all the Merkle proofs for the other shard come address pairs. And then when the transaction executes, it returns the values that are returned. So it seems simple and it's synchronous. You only are reading values, and I expect you could extend it maybe to be function calls, but maybe it can only be reading a data value in memory. And there can only be a single level of call graph. So in November 2019, Proto Lambda, who we've worked out, name is Didieric Loraka. And so he's come up with a mechanism where you have these commit capabilities. So, so each resource can have multiple capabilities. And so the idea is you submit a transaction on a shard in a slot, and it creates a capability on a resource. And that capability might be some aspect of it. Trying to actually understand, reading the words in the post, what those aspects might be was a bit confusing, but I think it might be, say, the hotel room has been booked. that could be, say, a capability. And so when you're getting this capability, you're locking the resource. And then on another shard in the next slot, you submit a transaction, and it contains a proof that that capability has been created in the state of the contract in that other shard, and that hence it's locked. And then you can execute some code that is done based on that capability being locked. And then you create a unlock capability. And so then in the original shard, in the next slot, you can then submit another transaction to say, hey, there's a transaction's gone through on the other shard, which is unlocking our locked capability. So now we can do something else. And so the post was a little bit confusing, but I think that is actually what it was driving at. And so the advantage of it obviously is that I guess it gives you atomic behavior. So it's happening all in one go between those two shards. It either both works or it both doesn't. And there was a timeout mechanism with it as well, I believe. So that, you know, if things fail, you're still good. It does seem to limit you, though. It didn't seem to allow for random function calls with, you know, parameter values and things like that. So it would appear to be a limited communication capability, but yeah, I'm not 100% sure because it was a little bit confusing. So I came up with a mechanism earlier this month called atomic cross shard function calls using system events, live parameter checking, and contract locking. And maybe I should have picked a shorter name. Anyway, this is based on our atomic cross-chain transaction technology. And so I looked at a lot of these other techniques and I thought, look, application developers, they don't want to have to deal with a lot of complexities. They just have something that they're used to, that when they're developing Ethereum 1 applications, when they're developing on Ethereum 2, they don't want it to be something completely new. And so they want to be able to have synchronous, composable applications that have, you know, arbitrary call depth. And so, you know, they want to be able to do things like this, where you've got an application, puts in a transaction, which does a function call. It maybe reads a value from one other shard, and then maybe it decides that it needs to fire off and write a value, so to another shard. And so you need to be able to do this sort of simple programming across shard, I think. And so when I was reviewing the technology, what I've realized is that for your execution environments, you need the following changes. Or also if you're using EVM, and so there's talk of having the EVM on either shard 0 or maybe actually on all of the shards initially and just abandoning the execution environment idea. So it will be equally applicable and needed for EVM if we were going to move ETH1 to the ETH2 shards. And so walking through these extra piece of functionality. So system event messages. So there's been a few other techniques that have used receipts of various sorts and even those commit capabilities. So they're things that are created that only the system can create, and they're not forgeable by other entities. And the idea is that I thought you could have, similar to how we have log messages at the moment for events in Solidity that are represented as events in transaction receipts, you could have special system events that are created. And so, for instance, if you did a function call as part of a transaction, then maybe the parameters that it gets called with, the return value, and all the other metadata to do with the function call and the transaction could be emitted as part of a system event. And then those events obviously could be referenced using Merkle proofs. Live parameter checking, so making sure that when there's a function call done, it matches, the parameters match what is signed in other transactions. having the idea that you can lock contracts. And so being able to have some contracts that are lockable and others that are not. And if you try and lock a contract that's not lockable, then it will fail. Have provisional state and contract locking. So essentially, and this is in many ways similar to the yanking proposal, where you've got your current state, which is locked, and then you've got your other updated state, which is provisional until you can return it to the current shard. So for this, you would have on the same shard some provisional state that is inaccessible until the whole transaction is completed. So as I said, this allows arbitrary call depth. So imagine you've got this type of set of function calls across shards, where you've got an application that is, having a complex set of calls. So in this approach, what you would do is you would have a special start transaction right at the beginning, and it would emit an event that would define the whole call graph of transactions that is going to go through. And then you would have transaction segments that would go through that are leaf transactions. So if we go back, we can see that there are the transaction on shard 3, shard 5, shard 6, and shard 7. They don't call anything else. So you could consider them to be leaf transactions. And then shard 2 and 4 call those leafs, and the shard 1 is the originating. So going forward, you can see that we've got these transaction segments on the leaf, on the leaf parts of the function call. And they will reference that start transaction to prove that they are part of this overall call graph. And then they will publish their results as part of the transaction receipt, so system events. And then the next segments can go in on the other shards, and they can reference the returned values, and also check that the transactions have gone through okay, and action goes through. And it again can make sure that it's part of the correct call graph. It can check each of these segments to make sure that they're correct, and also check the return values. Or each time when I'm talking about checking, it's a data value is passed in and a Merkle proof proving that the value is correct. So in the example, we had 2 of the shards ended up causing locking and having provisional state, and the other ones were essentially just reading values. And so you only need to send signaling transactions to unlock contracts on shards, shards and contracts that were locked. And again, you pass in Merkle proofs and data to prove transactions gone through, that it's valid, it hasn't timed out. And finally, you do a cleanup step. And so the reason for the cleanup step is that you need to use a unique ID to make sure that it's secure, and so that you don't have a burgeoning, growing state tree like you have in some of the other techniques. That clean step essentially removes that ID. And so it can be reused and also doesn't have to be held on to. So you'd probably want to incentivize that clean step. So the advantages of this technique seems to allow for arbitrary call graph, and you can do composable function calls. So you can come up with your application and divide it up into modules and execute it across shards. So there is some extra changes to the execution environment, such as provisional state and locking mechanisms, and there are some new transaction types. But similarly, I think a lot of these other techniques also require special transaction types to be introduced too, and locking as well. So there was one other scheme that we just didn't get around to looking at in great detail. Again, it's one of these schemes that's not really well defined, or at least confusing for me. It seemed to rely on Plasma exit games to work. Yeah, I'm not sure how that really worked. And it also seemed to relate to a previous era of Ethereum 2. So we put together a summary. So we've got some synchronous techniques and asynchronous techniques. For the atomic cross shard technique that I'm working on and the team are working on, we're going to add some sort of Ethereum ether transfer in for that. I mean, it could be used with ERC20 tokens to do value transfer. But yeah, if you wanted to do ether transfer right at this instant, it doesn't do it. Yeah, there didn't seem to be too much crossover there. I think another thing that if we were doing this talk again, we'd probably add how many slots does it take to execute, because I think that's another key area of interest. And so we've got coming up 3 more talks. So we've got Ethereum 2 staking that Darren Langley is going to tell us all about. We've got Ali Dori, and I believe he's going to be talking about IoT. And then Roberto, Frank, Joanne, and David, some combination of you are going to talk about ETH2 and formal verification using Daphne and where you've got to thus far. So I've talked quite a lot, but are there any questions? Far away, Horacio.
A lot of the, I mean, whenever there is a cross-shard mechanism, which assumes that there is a lot of communication between shards, isn't that tying all the shards together in a way that kind of negates the advantage of having shards?
I think, yeah, look, I think having the communication though is typically just via the crosslink. So essentially you've got the Merkle root of the current state of the entire shard and including transaction receipts, the whole lot. So you could almost think of it like a block hash. And so a lot of the techniques, that's all they need is that as far as communication between them is via the beacon chain. There is an awful lot of creating Merkle proofs and, so presenting data in Merkle proofs with transactions to prove that data is real and leveraging those crosslinks. That seems to be very, very common.
Yeah, still the original idea of shard was to distribute the state and transaction history. So that is still maintained. I think cross-shard communication is just a small overlap on that. So yeah, so it is not defeating the purpose of shards, I would say.
But still, all the shards are rather tightly coupled.
It's
a bit like they are
transaction, right?
Sorry?
It's coupled only by transactions. If there is a, I mean, they are linked. One can use cross links for verification. What exactly do you mean? They don't share the transaction history or something. So there's no such coupling. They don't share the state.
But it's a bit like, isn't it a bit like every shard is pinning to the beacon chain at every slot or epoch, or?
Yes.
Yes, correct.
So, I mean, the comparison that comes to my mind is whether it would be as performant as just having more, I mean, multiple EVMs or multiple new state histories in the current Eth1.
I don't quite get it. Multiple history pairs.
Like, imagine that now we have one EVM with its history. imagine that suddenly we may implement a fork, a hard fork, in which now we have 3 EVMs, one of them the current one, and 2 new ones with its own history. Would that be much worse than, or much better? Yeah, much worse than the whole history of having a shard with all its intercommunication.
So let's say a node will still have to maintain the full accumulated state, right? In your scenario, in the Ethereum 2 sharded world, a single node can maintain its shard state as well as the beacon state. I mean, this is disregarding the stateless concept for now,
Yeah.
but yeah.
Yeah, and don't forget that the validators are randomly allocated to shards, so they need to get everything statelessly anyway. But another thought is, though, if you've got, I mean, the thing about all of this is that your overall consensus protocol really is at that beacon chain. I mean, you do have the nodes threshold or signing doing BLS aggregated signatures on the shards. So I guess that's part of your consensus, but you're really, it comes down to what happens on the beacon chain. So by not having multiple, say, Ethereum 1 chains, you're only having, you're accumulating all your security and all your work towards having security on one chain, being the beacon chain. And, you know, so if you had, say, 2 proof of work chains for Ethereum 1 and somehow or other had cross communication between them, you'd have to split up the proof of work capability. So, you know, and in that way to be weaker.
Yeah, that, I mean, I totally understand and agree with the thing about the proof of work, but assuming that we managed to have, I mean, I guess I'm piling one assumption on top of another, but yeah, that's the thing. If we moved just to staking or to an alternative to proof of work, then yeah, okay, I'll think about it. Thank you.
Are there any other questions?
Yeah, so among all these approaches, how many have been, some are analyzed in a sort of, maybe not formally, but in another way compared to, let's say, saying this is an example of how it works and there won't be any deadlock, I think it should be okay, and so on. So what confidence can we have in these techniques?
Well, I don't see many analysis of these techniques, or at least they are not in public. Yeah, Joseph DeLong, as I said, he has a simulator. The purpose of that simulator is to analyze the transaction throughput of non-sequential receipts approach, but it's not complete. It's still work in progress. I have heard that the netted balance approach, people have, maybe from people from Ethereum Foundation, I think, they have kind of prototyped it and analyzed the specific question that one might have, that David asked about the burden of carrying Merkle proofs, or burden of the costly reading. So it looks like they have some optimizations which will say that it's not a burden, but there has not been any write-up or any document of that sort. I just heard over.
Are there anything? I mean, the simulator is that's a step towards
Yes.
having some elements to compare the approaches. So, are there any comparisons of the different approaches? And the second thing, which is something I really don't understand, if we don't have a clue about these methods, they've never been implemented or simulated, why are there so many? Why don't we start with one and say, okay, if this one works well, that's fine. And if it doesn't work well, we'll try to improve on it, but compare and figure out what was going wrong.
Yeah, that is when there is some stability and conceptual finality, right? So conceptually itself, there were disadvantages and people had to come up with new approaches to take away this conceptual disadvantage. For example, the non-sequential receipt had this receipt trees and Bitfield trees growing in an unbounded fashion. So the netted approach was specifically introduced to overcome those demerits. So once conceptually everything is finalized, then the step would be to simulate and see the performance, the security and stuff. Yeah, I think, yeah, so it's still.
So it's a sort of a follow-up question from what I understand Horacio was asking. I mean, it seems to me that in these approaches, there are solutions to some problems, but we don't really know whether they are real problems, whether they will occur in practice, and whether they will not actually, parallelizing things or using concurrency to compute something. It can be helpful sometimes, but sometimes it's better to do it in a centralized manner, because the overhead of communications will just be too overwhelming to gain anything. So there are known problems for which there's no point parallelizing, because you spend too much time sending messages around, and the best way to do it is in a centralized manner. So these are fair questions, I think, about the motivations of all these approaches. So why is the problem happening in practice? And then if it's happening in practice, yes, let's try to see the root cause of it and solve it.
But I think we are seeing the problem in practice being Ethereum 1 in that capacity. And so hence, how can we shard it is definitely what, so that's a result. So then I guess as far as, I don't think there is any hard analysis, or at least not that I've seen, of any of them. As Raghavendra is saying, there's simulations of some of them. So the technique that I've come up with, I'm busily banging out a quick and dirty proof of concept that'll simulate it and hopefully shake out some of the bugs in it, and at least allow us to have a think about it and reason about it a little bit. But yeah, I think there's a long way to go with these cross-shard techniques. Long way to go. That's, yeah. Are there any other?
Yeah, well, my point is, I would think rather than duplicating or adding new techniques every other week, or it would probably be better to try and get some good idea of how one of them or two of them work, and then clearly try to have a better understanding of the problem and what can happen in practice, and then later on maybe add new solutions or new features to it. But I think the duplication is, it looks weird.
I think the setup for the problem was also not stable, so it kept moving. So the notion of execution environment, the notion of slots, epochs, where to put the crosslinks. Initially, crosslinks were thought to be put at the epoch level, not every slot. So, but people started proposing for cross-shard communication. So even though there was no stable ground, and then it moved, people proposed some other things like that. So you're not operating on a stable ground. Right now, also the notion of execution environment is not very stable. People would want to proceed with a EVM-like execution environment, hard fixed on every shard, and then execution environment can be thought of. Flexible execution environment can be thought of a little later. That's one of the views. Yes, Horacio.
I would also add a bit of context there, which probably helps to answer Frank's observation. I mean, a lot of the cross-shard communication work has started only after someone in Twitter commented that about how amateurish is a lot of the design, or was a lot of the design, of course in F1 and even in F2. So a lot of that, of those techniques are still very undercooked, and now the goal is to bring known results from traditional computing science and distributed systems into the world of blockchain. A lot of those known results were missing. So hopefully, once though the well-known ideas start getting traction, the worse ideas will start falling away.
So I hope
for example,
so, but I mean, the problem
I'm
is
going to
sometimes
leave,
some,
by the way, Raghavendra is co-host.
sometimes some IDs, so we have to be careful that some IDs are not actually, I would say, ignored because someone else has a louder voice to push them. So, right?
Yeah, I mean, as long as people can simulate it and show the value of the idea existing or
I think it's a
proposed,
starting
so,
point, yeah, to just get
yes.
some ideas, how to compare them, and I guess you've got
Yeah.
some ideas. I mean, in the number of messages and so on, but everything we can say at the moment, yeah, it looks like it's not going to be efficient. It looks like it, but we don't have an evidence of it. So
Yes. Yeah, I think once the phase 2 draft takes shape, I think then all these techniques or new techniques will come up that will be put to test. But until then, these will stay in flux. That's what I sense.
It seems to me this is why we were talking about complexity analyses recently, is a lot of this stuff. I mean, if you look at the number of messages that are being passed around, for example, it does seem large. And, you know, trying to figure out which approach is going to be most efficient is something we really do need to spend time on, right? We really do need to do complexity analysis and see whether some of these things are just not the good ideas they appear to be. As I begin to go through the stateless Ethereum stuff, you have the same problems there where somebody has a good idea and then it just turns out to be horribly complicated.
Very true. Okay, if there are no more questions, we're already late by 13 minutes. Thanks for listening.
Thanks very much, Raghavendra.
Thank you.
Thanks, Raghavendra. Thanks, Peter.
Thank you.
thank you.
Bye.